Okay, let's get started. I want to just give a quick heads up. I know that we're a little bit behind on homeworks and whatnot. My TA had a little bit of a family emergency and whatnot, but he's going to try and chip away at a lot of that for the during this week. The homework solutions are all posted though. Homework 3.3 is due today. I'm going to post that solution. It's going to become live at noon, okay? So if you haven't done that, I would go ahead and do it soon because I'm going to put the solution up. What we're going to do today is we're going to talk about the operation of the exam, and we're going to talk about the topics of the exam, and then I'm going to let you ask whatever questions you want to me. I'm like right before class, before we get into it, I did have a question about getting together a set of like practice problems like we did in statics, and I'm working on that now, but we're going to be in here for a while, so we can probably do one of those practice problems together if you want, but we'll also have to have an understanding on what topic to do. All right, sound good? Now, just so everybody's aware, you know the attendance is worth 5%, homework's worth 35%, each of the 3 exams are worth 20%. So that gives you an idea on the grade. Let's talk about the logistics. So this is something I am doing differently than statics. I do not want to have a scenario where laptops die in the middle of the exam. It was one deal last semester when we had a 50-minute class. Now we have a 75-minute class. I'm not going to have that. I don't want that to, and honestly, it's really for your benefit. I don't want you to stress out about stuff like that. The thing about this is you don't need to charge this. This doesn't have a battery. So the exam's going to be paper-based on Thursday. So what I'm going to do is I'm going to give you not only a hard copy of the exam, but I'll give you a set of like scratch notes and whatnot, like a set of paper for scratch calculations. So you'll have more than enough room to do the computations for the exam. This exam is not intended to be time critical, especially in here. I would argue that this exam is probably no longer than the statics exams that we had last semester. And we had 50 minutes to do this. We have 75 minutes to do these. I still try and use the whole rule of 3. So I do the exam, and if I can do it in 20 minutes, then you can do it in 60 minutes. So whenever I finish preparing an exam, I actually take the exam and I time myself. So that wasn't an issue when I took it. I was able to finish the exam in about, I think it was 17 minutes. So it shouldn't be too much of an issue. So the exam is going to be very similar in format to the exams last semester. So there's going to be 4 to 5 short conceptual questions, okay? And when I say short answer, I mean short answer. I mean, last semester, we talked about this in statics, how we got some Shakespearean sonnets for some of the questions, and sometimes you only need like 1 or 2 words to answer the question. So they're not intended to be super rigorous. And then 2 to 3 computational problems. It is open book and open notes, so I'm sure you're going to ask if you can use your laptops to access the notes and whatnot. That's fine. One of the things I would suggest, given the nature of this class, I honestly think it's a good idea. I'm not going to make you do it, but I think it's a good idea to prepare a formula sheet. To put it all on one sheet, it actually forces you to study, and I think that in the end, the exam will go faster. I can't tell you how many times I've seen students prepare detailed formula sheets, and then while they're taking the exam, they never even look at it. Because by making it, you're studying. You may not think it, but that's what you're doing. So it forces you to go through that process of reviewing the material. But you can use anything that's on Blackboard. You just cannot use another individual. Okay, so that means no Chegg, no forums, no chats or anything like that. I had a situation a few years ago. It was during the pandemic where somebody said, "Well, I looked it up on Chegg," and I said, "Well, who do you think put it on Chegg?" People put it on Chegg, So no resources like that. But I think you have more than enough material for the exam. I'm not going to ask you any super complicated formula-related stuff on the exam. No derivations or anything like that. All right, let's talk about what's on the exam. So We've had 3 topics on the, or really 3 modules in the class. So the first is on the fundamentals of stress and strain. So make sure that you can compute normal stress and strain in basic structures, and you do need to understand like how equilibrium works, cutting sections, computing support reactions. I mean, this isn't a course in statics, but what's the prereq for this class? It's statics, right? So you have to understand that stuff in order to analyze some of these systems that we deal with in here. I do want you to be able to identify relevant properties on a stress-strain curve, and given relevant data or stress-strain curves, make sure that you can determine what's the modulus of elasticity, what is the proportional limit or the yield stress. Remember, the proportional limit is where it starts to go nonlinear, and then the yield stress is sort of that plateau. And remember, the yield stress can also be determined using an offset approach, like a 0.02% or 0.2% offset, or 0.002 strain. The ultimate tensile stress, and then the shear modulus. If I give you E in Poisson's ratio, you should be able to compute that. That's a simple plug and chug. And also make sure you have an understanding of what a factor of safety means. Our final 2 topics, and they are 2 topics, but they are damn similar, is an axially loaded member and a torsionally loaded shaft, because the loads are along the axis and are axidirectional. So because of that, the formulas and the resulting theory is very similar across the board. So, for instance, the axial elongation of a bar is PL over EA, and the angular twist of a torsional shaft is TL over GJ. And a lot of the expressions are similar and the methods are similar. So yeah. For axially loaded members, I want you to be able to compute the response, and by the response I mean the load, the stress, the strain, the deformation. Those are sort of the big 4 in this course. You go from load to stress, stress to strain, strain to deformation. Make sure you can handle members with a constant load or a varying load, and a constant area or a varying area. Remember, if those 2 parameters are constant, you just plug and chug. If either the load or the cross section varies, you need to integrate. Okay. Make sure that you can handle problems with indeterminacy, either internal indeterminacy or external indeterminacy, and make sure that you can handle members subjected to thermal loads. For torsionally loaded shafts, again, same idea. Torque, stress, strain, angle of twist, same, step-to-step relationship. Constant and varying torque or diameter. Remember, you're never going to have a torsionally loaded shaft on this exam that's non-circular. Okay, so that won't happen. But also make sure you can handle members that are indeterminate, again, either internally or externally. And finally, that you know how to analyze or utilize power-torque relationships. And then what I do, and by the way, again, this lecture is on Blackboard. You all, if you remember this in statics, what I like to do for the exam review slides is I like to package all the necessary formulas, or like the greatest hits, if you will, in this one slideshow. So what I did is I tried to pull all the relevant formulas and diagrams and put it all in a series of slides. So let's talk about fundamentals of stress and strain. So first off, stress-strain curve. We know the linear region versus the plastic and strain hardening region. Remember, if we get a strain out here and we unload at the rate of Young's modulus, but we lock in a permanent deformation. So if we yank on our axial bar to about, let's say right here, and we unload, it's going to unload at the same rate as the Young's modulus, and we're going to get a locked-in permanent deformation, however much that is. Stress is P over A. Strain is the deformation over the length, change in length over the original length. A couple parameters to keep in mind. Remember, what is Poisson's ratio? Poisson's ratio is the relationship between, if you take a bar and you yank on it, it is going to get longer, but it's also going to get thinner, right? And so Poisson's ratio is the ratio between the lateral strain versus the longitudinal strain. We throw a negative in there because if the member's getting longer in this direction, it's getting shorter in this direction. So we throw a negative, so the answer comes out positive. We know that normal stress and strain are related by E, and shearing stress and strain are related by G. I have a formula that relates those here in a bit. And don't forget the factor of safety, the relationship between the allowable stress and the actual stress. All right. For axially loaded members, I decided to just put it like this because I think this is really all you need for axially loaded members. So let me diagnose a little bit what's going on here on this slide. So I propose for any axially loaded bar, the total deformation is equal to any mechanical deformation plus any thermal deformation. Okay? So mechanical deformation is computed using either this integral. We integrate either the load or the area if those vary over the length of the member, or we just compute PL over EA if they're constant. So if you have a constant loaded area, it's just plug and chug. Varying loader area, you need to integrate. That's mechanical deformation. Thermal deformation, if we have a constant temperature, the deformation is alpha times L times the change in temperature. If the change in temperature varies, so if we have a bar and it's getting hotter on one end than it is on the other and we need to integrate, then we're just integrating alpha times delta T from 0 to L. Torsion, I got a little bit more going on, although the angle of twist expression is the same. We have the angle of twist is either TL over GJ if we're dealing with constant torques or J's, or the integral of T over GJ, we have a varying torque and or J. Here's our expression for the shear stress, TR over J. So the shear and strain would just be that divided by G. And then here's our J formulas. J for a solid shaft, J for a pipe, and then sort of the two, I guess, sort of remaining expressions that we need to deal with are our shear modulus expression. So if I give you E and Poisson's ratio, what's the shear modulus? And then the power-torque relationship. So if I have a motor, and that motor is supplying power to a given engineering system, it's going to do so with a torsionally loaded shaft. And so there is a relationship between the amount of power being delivered and the amount of torque in the shaft. And we need to understand that so that we can size that shaft, because we don't want to turn the motor on and snap the shaft, right? So we take power equals torque divided by 2 pi n over 60 if we're dealing with SI, 2 pi n over 33,000 if we're dealing with US units. And the difference is that if we take 550 foot-pounds per second, that's a horsepower. So 550 times 60 is 33 grand. That's why we have 33 grand in US units and 60 in SI. All right, that is everything on the first exam. So with that, I'm going to shut up for a second and see if there are any general questions, anything that's on your mind, anything you want me to go over, anything you want me to look at. Let me know. The floor is yours. Too early, still settling down from previous celebrations. Yes, sir.
Can you go over the unit question I asked yesterday about why I didn't have millimeters for the giga?
Okay, so one, let me say that. So let me answer it this way, because so the question is about SI units as it relates to torques and stresses and things like that. So a couple things that I want to illustrate to everybody. So let's start off with notes about SI units. And if I don't answer your question, tell me, okay? So, okay, and in order to address this, I want to use what is arguably the most involved units expressions, and that's probably something like this, okay? So, whenever you're doing mechanics-based problems, one of the things that I think is important is that you convert everything such that you have a consistent force unit and a consistent length unit. Okay? So let's say that we decide that forces need to be in newtons and lengths need to be in meters. Okay? So what that means is that torques need to be in Newton meters, lengths need to be in meters, G's need to be in pascals. Why do G's need to be in pascals? Because a pascal is a Newton per millimeter squared, and J needs to be in meters to the fourth. So what that means is that if you're dealing with a problem where this isn't the case, okay, where you're given, I don't know, the J is in millimeters to the fourth, or the T is in kilonewton meters or something, you're going to need to deal with that, okay? Now, this is a consistent unit system, okay? To be honest, I don't really like doing SI problems with torques in this fashion, okay? I don't like that, okay? Here's the system that I prefer, and I want to tell you why, okay? So this would what I would call base units, and we're going to call this Dr. Mike's preferred units. Okay, so what I prefer is that your force is in kilonewtons and your length is in millimeters. Okay? Now, let me explain why. Okay? First off, let's talk about the torque. So, your torque, if you're going to do this, your torque needs to be expressed in kilonewton millimeters, right? But here's the thing. 1 Newton meter equals 1 kilonewton millimeter. Okay? Now how am I doing that? Well, what am I doing to the kilonewtons? Well, I have K, which is times 10 to the third, right? And I have milli, which is times 10 to the negative third. So they cancel each other out. So a lot of times we're given torques that are in Newton meters, and it's really easy to just say, that's kilonewton millimeters. Okay? So 1 Newton meter equals 1 kilonewton millimeters. That unit conversion gets real easy. Okay? Lengths, I think lengths are really easy to do conversions on. You know, like 6 meters is 6,000 millimeters. I think it's really easy to just do that. So I don't think that's a big deal. Okay? Now, G's, a G needs to be in a gigapascal, which is a kilonewton per millimeter squared. Now, how do you get that 1 gigapascal is a kilonewton per meter squared? Like, how do we determine that? Well, so 1 gigapascal is 1 kilonewton per millimeter squared. What does the prefix G mean in SI? What is that, 10 to the, say it again? I didn't, somebody. 10 to the 9th, right? So we have K, which is times 10 to the third, right? But then on bottom, we have 10 to the negative third, but we're squaring it, right? So 10 to the negative third squared is 10 to the negative 6, but it's on the bottom. So we have 10 to the third and 10 to the 6. That's where we get the 10 to the 9th, okay? The reason why I like kilonewtons and millimeters is a lot of times in SI units, G values are given in gigapascals, right? That's usually always the case, okay? Now the other reason why I like these preferred units is because of J, all right? How many of you did some of the last homework problems with J in meters to the fourth? How many did that? What happened to your J values? Like, what are they like when you use J in meters to the fourth? They're really small. They're so small that it's actually kind of hard to get the necessary numerical accuracy, and so you have a lot of rounding problems and you have a lot of like quirks with that. So, but how many of you operated in millimeters to the fourth? So you get really big numbers, right? It's because you're taking a millimeter and you're raising it to the fourth. If you're talking about a cross section, you're going to get a really big answer. Now, what ends up, so the reason why I like these preferred units is because it's easy to do this unit conversion. It's easy to do this one. We tend to get G values in this unit anyways, and this deals with a much more consistent answer. Now, another note is that if you do it this way, your stresses are going to come out in gigapascals, and they are probably going to be small. But they're not going to be so small that it's like the J values where it's like times 10 to the 9. So whenever you use this preferred unit system, your stress values are going to come out a little small. So because they're coming out in gigapascals, we tend to express stresses in SI units in megapascals. So I would just plan to take your stresses, whatever you get, and multiply them by 1,000 to turn them into megapascals. It's a more manageable unit system. Say what you will about US units. US units, I tend to deal in kips and inches, and everything's kind of manageable because the stresses work out pretty well, the deformations work out pretty well. So maybe I should also mention that, is that over here, I kind of think, I mean, for those of you that are enemies of the U.S. Customary system of units, I do think that from a mechanics and materials perspective, numerically, you do tend to have some pretty manageable numbers when you're dealing in U.S. units. That's just the truth of it when we look at a lot of engineering problems that we deal with. So that's just the truth. That's kind of my suggestions for you for base units. Now, to go back to your question, because you were asking me about what you had done on your particular homework assignment, and I think what you were doing is using a base unit system of newtons and millimeters. So you were ultimately, but here's the thing, you ultimately did it correctly, but I think you probably did more work on the unit conversion side than necessary if you just sort of did this. Like said, okay, if I put all my forces in kilonewtons and all my lengths in millimeters, then everything sort of washes out in the end. Whereas you had put your forces in newtons and your lengths in millimeters. So you did it right. I mean, it's not like you did anything wrong, but you probably had a little bit more work to do on the unit side. Did that answer your question?
Yeah, so I got a little messy with the unit conversion.
Yeah.
Going through there, trying to figure out what equals what.
Yeah, but I think, so when you use newtons and millimeters, you got stresses in megapascals, which is, in stress land, that's actually what you want. But it also, your G value needs to be higher, and, you know, I tend to like this because it's easy to remember that, and you actually don't need to do any conversions here. So, I mean, it's engineering. We tend to put a lot of force on system, and we don't get a lot of deformation. So, when you use a lot of higher grade, research grade finite element packages, they actually don't have an inherent unit system built in, and you as the user have to sort of keep track of it yourself. And there's sort of two schools of thought in that. I kind of prefer that because then I can do what I want. I'm not bound by some limitation of the software package, but you do have to be good with your unit conversion system. If anybody ever has any experience with ANSYS or Abacus or anything like that, yeah, you gotta keep your units straight. So you might be dealing with that maybe your senior year. Okay. Any other questions? Did this help? Everybody okay with this? Okay. Did any other questions? I mean, let me tell you this. I guarantee you this stuff causes the exam average to drop a couple points. Just getting units wrong. So being straight with that will make your life a lot easier. Yes, sir.
Last night on the homework, you couldn't find the maximum angle of rotation.
Yes. Or you had to find the angle of twist at the end.
Yeah.
Yes.
its T value, it's J, and I got
An angle.
an angle. And then I did it with the pipe again with its, and I got the same angle.
Yes,
Why?
because you said that at the very beginning. So how did you solve for the two torques? Now, this is a very good academic, intellectual exercise. So this is a really good question. So what he's saying is, on the homework assignment yesterday, that you took the properties of the bar and computed a twist and got an angle. Then you took the properties of the pipe and computed an angle, you got the same answer. All right, now I want to go back to the very beginning of the problem. How did you solve that problem? You used two equations. The first equation was that the torque in the bar and the torque in the pipe, when you added them up, had to equal whatever was applied, 400 newton meters, whatever it was. But what was the other equation that you used? That they're equal, that the rotation of the bar and the rotation of the pipe are equal. Now think about it physically. What are you doing? You've got this solid core and this pipe, and you are taking it and twisting it. But you're twisting all of it, right? So imagine it in your hands. Here's this, and you're twisting it. The angle of twist is equal for both of them, right? If the pipe rotates 12 degrees, then the shaft rotates 12 degrees as well. So if you're doing that and thinking that you did something wrong, it is 100% the exact opposite. The fact that you got the same answer shows that you did it correctly. You should get the same angle of twist in both elements. Think about the physics of the situation. Think about what you're doing. It's the same thing with a composite column. If you take one of those composite column problems that we did, homework 2.2 or whatever, right? Compute the PL over EA for the aluminum and the PL over EA for the brass. You will get the same answer because that's what you're doing. You're taking it, you're squishing it, you're going to get the same shortening in both elements. That's the check that you're doing it correctly. Now, I would argue that assuming that you were tracking your decimals, you got the exact answer. If there was some rounding, maybe it was a little different. So, yeah.
What's the application of having a bar with a large space in between it and its outer pipe?
That's for you mechanical engineers to figure out. Honestly, that was going to be my first statement, was the thermal expansion, or if there's some, fluid or lubrication that needs to go in between them. But beyond that, mechanically, let me say this. So mechanically, let's talk about mechanically. What happens, let's think about this numerically, okay? So what happens if I take a pipe and I make the diameter larger, right? What happens to its J value? Its J value goes up. Tau equals TR over J. The R value is going up, right? But the J value is going up as well. What my point is that I would argue that as the shafts or the pipes getting bigger, the torsional stresses are going down, okay? So if the stresses are going down, then I can use a thinner pipe. So maybe by making it a bigger diameter, I might be able to make it thinner, okay? So mechanically, there's probably a benefit. Thermally, there's probably a benefit as well if it's being heated up. Beyond that, probably not much benefit, if I'm being honest. So we're going to have a very, very involved discussion about beam proportions later, because I don't care if it's a building, a bridge, a car, every single engineering system I've ever seen has something in it that's being bent, and bending stresses and composite bending stresses are a whole animal in and of themselves. So we're going to have a very involved discussion about that. You're thinking like an engineer, sir. I like that. You're also on time. Hi, I'm Greg Michelson. I teach mechanics and conformal bodies here at Marshall University. How are you doing?
Pretty good. There's no street parking this morning.
There wasn't when I got here.
Yeah, it wasn't at 20 after 8.
Speaking of thermal loads, that was a burn. No, sorry. materials. I love this job. All right, come on. Any other conceptual questions? This is really good stuff. This is, I mean, this is the stuff I want you thinking about. Because here's the thing: thinking about this stuff, it's like it's almost like you're going to do fine on the exam. It's like I want you thinking also like what's past the exam, because you are. I know this is an odd thing to say, but I know you all are trying to be engineers. I want you to think about that stuff. So it's kind of important, right? It's just your whole goal in life and everything. Let me ask this to help guide some questions. We have 3 topics on the exam. Is there any topic you're worried about the most? The torsion, the axial loads, or the fundamentals? Like, what if there's any one that was like, I didn't get that? Oh, okay. You got all of it. Yay.
The axial took the most work, I guess.
The integration? Yeah, I can appreciate that. One thing I will tell you, okay, here's one I'll throw at you. We are not going to have integration on the exam super in-depth related to torsion, and we'll tell you why. The reason why is because the J properties, the integrals, can get a little longer when you have integration related to the fourth and whatnot. So we're not going to have any like super in-depth torsion integrals. Axial is a little different because the resulting math isn't as in-depth. Okay, so if there's any integration or any calculus on the exam, it is far more likely to be an axial land than it is torsion land. Doesn't make it any different. It starts becoming, like when you start putting it with J's and whatnot. I don't want this to be a math test. That's my point. I'm not saying you get to avoid calculus as engineers, but this is an engineering course. This is not a math course. So I will say that. What? What'd you say?
I like where this is.
No math.
Multiple choice?
Yeah, no, we're doing math on the exam.
I thought it was just gonna be like, if I stretch this pipe, it doesn't get stretched.
I believe you're looking for a class in the philosophy department.
We are in the business
We're in this
right now.
business. Yeah.
This isn't the philosophy building.
No, that's where we used to be, wasn't it?
What?
That's where we used to be, wasn't it?
That's probably closer, yeah.
So now, like, psychology's gonna get in our business.
Okay. Can we look at homework 2.2 problem 2?
2.2 problem 2. All right, I like it. You want me to pull up the solution?
Yeah, I just don't understand how to make B redundant because I did it like a different way.
Okay, let me see. I'll tell you what, let's do this. Oh, goodness. What might be easier, since I brought my book, is let's go through it together. What problem was it?
It was 2.4-15.
2.415. All right. Okay, I have it here. Sandwich the screen here.
It was part B.
Part what?
B.
B. Okay, let's see. Okay, so 2.4-15. Okay, so just to remind everybody about the problem, so we had a steel pipe and there was a plate right here, and then we had an aluminum pipe. Like this, okay? And we had a P and a P. Hold on. We had this, and we knew that this dimension was L, and this dimension was 2L. I believe that's correct, right? Okay. And this was, let me see, this was support A, this was support B. All right. Now I'm going to, let's see, I'm going to take a picture of this data because I'm actually going to use the book to, hold on. Oh, goodness. Where's my camera? Because I'm going to use my book to prop this screen up. Okay. So I want to first make sure that we have an understanding of how to handle external indeterminacy, and then we're going to start looking at this problem, okay? Now I'm going to put my little thought bubble over here. And I want to ignore this problem for a second, and I want to give you a problem that's maybe a little more visceral and a little easier to follow what's going on, okay? So I want to take a beam, okay? Now here's a beam, and let's put some loads on it. Let's put this, put a load here, put a load here, put a load here, like all sorts of loads on it. It doesn't matter. Okay? Now, let's go back to statics land. Does anybody remember what we call a beam with a support condition like this? Anybody remember we have a name for that? When we have a hinge on one end and a roller on the other. Remember? What's that again? That is right. We call that a simply supported beam. Now let's go back to statics land, okay? Three equations of equilibrium. We have the sum of forces in the x direction, the sum of forces in the y direction, and the sum of moments, right? And then we have three unknown support reactions. We have a vertical reaction right here, and a vertical and a horizontal right here. So this would be a problem that we would say is statically determinate, right? Make sense? Okay, so that's a determinate problem. What if I do that? Now it is statically indeterminate, right? There's too many unknowns, okay? Now, the equations of statics, or the principles that we learned in Engineering 213, are simply not enough to analyze this problem. Do you think that we have these problems in real life? Have you ever driven over a bridge that has a pier in the middle? Spoiler alert, yes, you have, right? I guarantee you have. And we have to analyze that. How do we do that? We use what we learned in this course, okay? Now, what we need to do first is we need to pick one of these rollers and treat it as a redundant. Now, for the sake of discussion, what I'm going to do is pick the roller in the middle. All right? So, the first thing I'm going to do is I'm going to analyze this beam with all of its loads, all of its original loads, but with that original middle roller gone. This is a statically determinate problem right now. Now I want you to think about this class. What is the name of this class? Mechanics of what? Deformable bodies, right? I propose that if I have a beam and I've got loads acting like that, that beam is going to deform. If I'm sitting on this table, it is going to flex downward, right? So if I use my little green pen right here, the beam probably going to deflect something about like that. Is that a fair statement? Okay? So right here, where that roller is, we're going to get a deflection. Let's name these. Let's call this A, B, C. We are going to get some deflection at B. Let's make up a number. Let's say it's 2 inches. It doesn't matter. Let's just say it's 2 inches. Now what I'm going to do is I'm going to do a separate analysis. A separate analysis is going to be this beam. Oh. With all those gone, but instead I have a load here. Now, with this beam, what's going to happen is it's going to deflect like that, isn't it? It's going to come and deflect upwards. And I want to know what that force needs to be to push it upwards 2 inches. Because here's the thing. What happens when I superimpose these two analyses? When I take this analysis and add it to this one. If I take this plus this, I'm going to get this. What's going to happen is the deflected shape of this beam is probably going to look something like this. And what is that deflection going to be? It's going to be 0, right? So, the way that we handle external indeterminacies is we choose a redundant, and we do 2 analyses. One with all the original loads with that redundant gone, and another with none of the loads but that redundant. And we figure out what this reaction needs to be such that its deformation equals that, so that when we superimpose them, we get this. Now, before we talk about this particular problem, does that make sense? Does that concept make sense? Anybody have any questions about that? Because that's kind of important. Now, before we talk about that problem, I do have one other point I want to make. I chose the reaction at B as the redundant. And I did so because that seemed to make sense visually. But what if I said, now I'm going to choose the reaction at C as the redundant? Would I have gotten different answers at the end of the day for all the reactions? No. That would be a completely different problem, and it'd be a completely different, set of calculations. But in the end, the 3 reactions I get for here, here, and here would be the same. Because just as the deflection here is 0, the deflection there and the deflection there is 0. So one of the problems with external indeterminacy is that there are multiple ways of doing the problem, and we can all do them different ways and all get the right answer. Which is why on that homework assignment I said, make B the redundant so that we're all doing it the same way and so that it's easier to grade and easier to structure the calculations, right? But very easily, some of you could have said, I'm not using B as the redundant, I'll use A as the redundant. You'll still get the same stresses at the end of the day. You'll still get the same deformations at the end of the day. Does that make sense? So what we're doing is saying this equals this plus that. That's basically what we're doing. So we're going to do the same thing here. We're going to say, this is keyboard, I'm telling you. We're going to say that this equals this plus this. Now, I propose that this system over here is going to result in a net displacement at this point going down, right? That the system started here and this load's going to push it down. So we're going to get some deformation. Oh, this screen, I'm telling you. We're going to get some deformation like this. And so we're going to need to figure out what is this such that that deformation pushes it back up. Does that make sense? So again, it's kind of the same idea, that this equals this plus that. And so if we look at, we'll call this system 1. We'll call this system 2. So for system 1, so we know that the axial force in the steel is 2P, and the axial force, what's that lower bar? Is it aluminum? Yes. Is what? So what if the axial force in this bar is 2P, what's the axial force in this bar? I'm curious. Anybody tell me? How about this? Here's the bar, right? I'm holding the bar right here, and I'm grabbing it here, and I'm yanking it down. So this part is experiencing tension. What's this part experiencing? Nothing, right? So this axial force is 0. All right. And so we know, hold on. So we know that this is 2 times 12, which is 24 kips. This is, of course, 0. Now, I don't think we were given lengths for the bars, right? But that actually doesn't really matter. So we do know that this is L and this is 2L. So often in indeterminate land, we can just keep it as L, or if you want, we can assume a value for L. Because ultimately what's going to happen is the L's are going to cancel. Okay? So what we'll do, we'll leave it symbolic. So we'll say L steel is L, E steel is 29 KSI, and A steel is 1.03. So delta B is PS L S over ES AS, which is whatever P over EA is times L, right? With me so far? So that's system 1. So I'm going to make up a number unless somebody wants to correct me. Let's say it's like 0.56 L. I have no idea if that's correct. Like I'm just throwing something at the wall and seeing what sticks. And so now, when we look at system 2, we know that P steel equals P aluminum is RB. We know that delta B is 0.56 L. All of the other properties are the same, and so we just sum up that deformation and solve for RB. Now, We can carry this out if you want, but I don't want to waste time if there's questions about other things. So is everybody with me so far and kind of understanding the process? What about you? Because you asked the question first off.
No, yeah, that I made
Okay.
it clear. Thank you.
All right. Do you have a question? Okay. You were stretching. Axially elongating your arms.
Yes, I most certainly was.
Oh, man. Just do me a favor and please don't get stressed out over this exam. What's that? That was a really bad joke, right?
We heard words.
You heard worse? Okay. I'll have more, by the way. I'll see if I can test that theory. Oh, Lord, I love this job. Okay. All right. We still got, a good bit of time. We still have close to 15, 20 minutes. So, any other questions? In all seriousness, how are you feeling about the exam? Feeling stressed? Feeling? I didn't mean that to be a joke. I'm saying. Nervous? Comfortable? You tell me.
Convenient that I got moved back.
What's that?
Convenient that I got moved back.
For you.
Yeah. But it is for you too, because I think in most of our cases, that might have been it. I mean, that would have been just straw that broke the camel's back.
Yeah, I haven't passed a single exam yet.
I would have actually.
I don't know yet, but I felt that.
You telling me if the exam was today that you'd have hit your proportional limit at that point?
Oh, I was thinking.
Yeah.
I told you there'd be a worse joke. I promise. Just for the hell of it, like problem 5s or 4s, could be like solve for X.
That'd be pretty darn groovy.
Yeah, that'd be all right. Oh, I'd be so mad if that were the case. Oh, man.
I'm scared. I'm a little worried now. I get to grade, I get to grade 50 exams after we're done with this.
What?
No.
What
else
you
would
know
you
how
have
to
me
make that
do?
easier?
What's that?
Have the exam be easier. There's less to check.
We had this discussion about the model last
We've already had this conversation in statics where there were 60 people in statics, so.
Yeah, see, the workload's getting easier and easier. Everybody at the end, we'll just lump
At the end, you still have 2 more years of college, man. This is not.
You sure? You sure?
Well, that's up to you, I suppose, In all seriousness, and I'm not trying to sound melodramatic, but to me, statics is important, and it lays the foundation for what we do as engineers in a lot of arenas. But to me, this is where engineering really starts. This is where it really begins, because you're now able to look at a system and go and look at a problem like what Mr. Hall was talking about. He said, wait, why would you build a shaft this way? Why would you size it in this fashion? Why would you have the gap? And we talked about problems where, if you had a given way of arranging a shaft, let's say, how would you do it and why? Relating what we did in lecture 1 to factors of safety and how, if we have the bar supporting a weight over, your little kitty cat, is that going to be safe or not? And you're able to, oh, I get it. I get what we've been doing for the past 2 years and what I'm about to start doing for the next 2 years and the rest of my career. So I really want to make sure that you're understanding it. And if you understand this, I really think the exam's going to be fine. It's the concepts that are probably the most important. That was a mouthful, I know. Now, we have about 15 minutes. I am happy to give you the gift of time if you want, but only if there are no more questions, because I want you to get value out of the review session. So. Going once. Going twice. Yes?
I'm just playing.
Well, let me say this. If you weren't, on Friday, there'd probably be one more parking spot given the air being let out of his tires, you know. You're keeping us here, man. All right, there were a couple people that came in late.
Hey, I wasn't the last one.
I'll pull up the QR code one more time. How am I going to miss that paparazzi jacket? Come on. That's all I got. We'll see you on Thursday. Best of luck.